Okay, so starting off with some carboxylic acids. How this first part goes, and I think that with the organic chemistry this quarter, it makes a lot of sense. 118B, you were like stuck in between knowing the basics of 118A, and then there were just awkward, yeah, like alkenes, alkynes were similar, but then you like really changed gears and you went to like the Diels-Alder, and like benzene rings have like no similarities whatsoever to alkenes and alkynes, and then you jump into carbonyl. So it's just I felt like it was kind of all over the place for that course. But for this course, a lot of it makes sense, and the reactions are super similar in the very beginning. So we have carboxylic acids. It's kind of a play on our carbonyls again. So you have like a C double bond O, and we have things that like to attack that carbonyl carbon. So at this point, another reason why it's good to do the class like sequentially, take your aldehyde and ketone knowledge, and we're just gonna move from that. And I think that's gonna be super helpful. After we do carboxylic acids, there's something called the derivatives of carboxylic acids. And what we'll do, we'll actually make these little flow charts to show you like, okay, here's like the motherland, right? This is the main reaction you need to know, and then everything after that just kind of branches off of that. So that's kind of what we're gonna do today. All
Gotcha.
right. Okay, and I'm just gonna pop off the camera for now, and then I'll probably jump back in a second. Okay, so all right, so I have a little worksheet here for us, but I always like to put this in here just to have something ready for us. So if we're gonna like do some practice problems, you can clearly see like, awesome, cool, like I already got some naming thrown at me. Here's like kind of the vocab and the fill in the blank and ranking and acids and bases, and then here's like this is what we're striving to get to, right? So you have like your carbonyl reactions, boom, there's an acyl chloride, here's a carboxylic acid, and then different types of reagents along the way. And we kind of just see how those reactions go. But again, these are just practice problems, and I love practice problems, but I think for this first part, it makes sense for us to kind of go through how to make carboxylic acids, kind of like what we've always done with the different reactions in the past. So how do we make them? And then after that, then we can jump into all the different types of reactions from there. So let's get started. All right, so for the carboxylic acid, there's a couple things we need to know. One, we have our H plus back, and then we have some sort of nucleophile. Like you saw with your ketones and your aldehydes, if you have any carbonyl and you have an H plus, then you know your first step is always going to be have that oxygen up on top, go grab a proton. And the reason is because, again, moving forward in this chapter, our nucleophiles are going to be more on the poor side. You're going to see things like a methanol, an ethanol, something that has lone pairs that is reasonably basic. But I caution you to compare and contrast the differences between something that's a poor nuke versus something that's a stronger nucleophile. So if we do have something that's on the stronger side, right, the mechanism works a little bit different, and that's where you can kind of double the amount of reactions that show up in the class. So if we have a carboxylic acid up on top with H plus and a nucleophile, first step, of course, is that oxygen grabs a proton, kind of charges it up. You have resonance along the way. And then I'm going to ask you a couple questions moving forward just based on that. Okay, we're going to compare and contrast acidic versus basic conditions. Okay, so let's say that was our first step, and then we have our nucleophiles ready. Of course, what is our nucleophile going to want to do at this point?
It's gonna want to attack the carbonyl carbon.
Yep, perfect. So then this is going to come into here. And the reason why I started off with the general example first is because this does translate to a lot of different reactions. So you get to this intermediate phase here, and I think this can be the trickiest part because this is where you're going to have three oxygens all at once, depending on who the nucleophile was. So you get to this point, and it can be kind of paralyzing because you're not sure which of those is going to be the leaving group. And so my rule of thumb is if something is new, it's going to stay. That's not going to be our nucleophile. And generally, these two things are interchangeable. So see how they're both OH groups? You can actually use either of those two to be leaving groups, and we're ultimately going to try and get it to go and try and to get it out of here. Now, this nucleophile probably came in with a proton attached to it, right? Like, for example, I'll just throw in like an ethanol. And so when that came in, then your oxygen is going to be fully positive. And then, like I said, there's three O's there. And so what we need to do, we just need to take one of these guys and we need to try and make a better leaving group. So again, very similar to the ketone and aldehyde reactions where We take one of our neighboring groups, it reaches over for a proton. This is kind of like intermolecular type of reaction. And so now you have an OH2 plus on the right-hand side versus just your standard OH group. And then that makes a better leaving group. So one thing we really like about carboxylic acid reactions and generally, a general schematic that you can think of, I used to call it the replace the box method. I kind of got away from using that for a couple of years, but I like to think of this as a replace the box method as you got a carbonyl up on top that's generally just going to stay there in your final answer. And then all we're doing is we're just replacing the box. So if we had an ethanol, then you're going to have this O take the place of that one, and it's going to come along with two friends for the ride. And if you think of it super simply like that, then all of a sudden the clarity of the number of reactions you're expected to know just becomes so much easier. Rather than doing one reaction at a time and trying to memorize everything, this is the general flow of how everything's going to go. So this is going to be replaced. There's our good leaving group. And then, of course, I think the last couple of chapters, we really moved into, if we have the ability to at least form and do something to leave, we prefer that instead of just forming the carbocation. Generally going to be a little bit less preferred to form the carbocation. So that's why that O comes down, reforms your carbonyl. And so now you have your carbonyl up on top. Then you have your new group, so we'll call it the nucleophile. It lost its H. So again, if it was a replace the box method, it would be this oxygen with the two carbons. We replace that box with something new. And then up on top again, you can imagine the H plus conditions that we were in, probably in some type of HSO4 minus conditions. So then this is going to come swing here. And that's how you get your nice clean carbonyl group again. And depending on what our final answer is, you get a different derivative of the carboxylic acid. So the carboxylic acid is kind of like our motherland. This is the most important fundamental reaction. And then from there, depending on who the nucleophile was, you can have an acyl chloride, you can have an anhydride, an amide, an ester. There's a lot of different functional groups. And that's kind of where we go sort of one step at a time. And then each of those derivatives will also have their own set of derivatives as well. So in this case, that's the top one. And we'll do an example. I think one of the most popular reactions that could show up on your exam is something called trans-esterification. It's so popular. It's got a lot of points, and mechanistically, you have to follow a proton just back and forth. It could be upwards of like a 20 to 30 point mechanism. So, but it's not hard. If you just kind of follow what we're doing here, I think it's going to be valued to you. You're going to get a lot of points. All right, but importantly, compare and contrasting this acidic conditions versus now kind of throwing you, this is where I challenge you because again, you've built such a good foundation that I think that I could throw a reaction at you, and even if you haven't done it before, just kind of see how you respond and go from there. So let's say we have this. It's our step one, and then our step two is H plus. So a little bit different, right? Up here, both of those were thrown in at the same time. There was no clear like, hey, step one, step two. Now I'll let you take it away and just kind of predict what the first step is, not necessarily predicting what the final answer is.
Okay. So we're adding basically, okay, so we're adding lithium, which means generally our double bonded O turns into an OH, and then from that carbon we have the two carbons on the lithium, right?
Yeah, so you're saying the two carbons and the lithium
Mm-hmm.
kind of swinging over here. Is that what you mean?
Yes, and then
Yeah.
everything pushes up.
Yeah, for sure. So, and I love that because we did that with carbonyls, right? We did that with an
Mhm.
aldehyde. We did that with the ketone. One of our limitations of carboxylic acid reactions, and this is where they get kind of clever, and I would say a lot of students will falter, is we end up getting so comfortable and so used to attacking inside this carbonyl carbon that that's all
Mhm.
we end up wanting to do. So it's a good suggestion with a strongly basic nucleophile if it's too strong. So those examples would be like RLIs, your Grignards,
Right, we
RMGX.
add the H.
We can grab the H from the OH because, as you're preparing for your MCAT, so, you don't have to memorize pKa values per se, but just tying in a couple different trends, right? Like this pKa, and with your professor, she loves pKa. So, I mean, this is just spot on. But the pKa being low means that it's a greater acid, right? So it's going to be a stronger acid. And if you mix it with a strong base, then rather doing that nucleophile electrophile combination hitting in here, it's going to be much more attracted to that proton. So now, you have a positive here, partial positive there. Here's your bond. Unfortunately, we're not going to get kind of what we would hope, right? So I would want to bring in that extra carbon, kind of do like a Grignard reaction, push that up to an OH, like you said. But actually, what we get here is that you end up getting an O minus, and then that's basically it. And actually, this is a tricky question because then the O minus will actually go grab the proton here, and then you end up just back again with the carboxylic acid. So that's kind of a nasty problem. What I think would be probably more likely to show up would be something like this, and then there's no H plus workup, and so you actually just left with an O minus, and it's kind of not satisfying. You're kind of like, really, that's it? And then you didn't get the credit, and it's like, oh, that's a bummer. I wish I could have got 5 out of 5, right? And you end up getting, 2 out of 5.
Right.
So that's how that one works. Again, there's really not much more beyond that, but I would say just kind of have this in your back pocket at all times and be on the lookout for something like that to trick you up. But for the most part, especially with your professor, you can expect to live really a lot up here in this land.
Gotcha. Okay.
Right. Cool. Okay, so now we'll do the reactions and how to make some carboxylic acid. So I'm just going to throw a question at you. Anything on the top of your head? I know you just graduated, so maybe there might not be one that just jumps off the walls, but anything you can think of on how to make a carboxylic acid from the experience you have so far.
I think it's a secondary alcohol with the Jones reagent, right? That makes us go all the way to carboxylic acid.
Yeah, there you go. That's a good one for sure. So bringing in Jones is fair game. And again, they may go over some review problems, but generally they don't. They kind of just jump straight in. And it's sort of expected that you need to recall anything that's pertinent from 118A and 118B to help you here for the first exam for 118C. Secondary with Jones is going to make a ketone.
Mm. So then a primary gets us all the way to Jones
There you
with
go.
the
Perfect.
carboxylic acid. Yeah.
Good. And then what if we do PCC? What happens if I throw PCC in the mix here with the primaries and the secondaries?
We'll still get to a ketone with the secondary, but a primary will stop at an aldehyde.
Perfect. Yeah. Good review. PCC, Jones, kind of alternating. Let's do the first couple here. So ketone up on top. You get a ketone for the second one as well. And then let's change the third and the fourth ones to primaries. Those are primaries now. So your third one there is going to form into a full carboxylic acid. And then the last one is going to form the aldehyde. And then just to double check, of course, there's only 2 carbons there. And then up on top, I still have the 3. So things look pretty good. So we got ketones up on top for secondaries, primaries here with Jones, carboxylic acid, and then here at the PCC. And again, this is going to be helpful for your synthesis problems too, because they'll probably start you off with something that's not a carboxylic acid. And then after 1 or 2 steps of making one, then you have to do the reactions. And that's how they can make like 4 or 5 multi-step synthesis. Okay,
Right.
couple other ones just because it is important to review from 118B and see what's helpful. So another one that we can do is KMNO4. So if I have an alkene, now you're probably going to recall something like ozonolysis. If I react this with ozonolysis right now, the only issue with that is it's going to make carbonyls like a ketone or an aldehyde, right? So if I do an O3 here, it's going to chop this right down the middle. You add a carbonyl on this side, and you got a nice formaldehyde over here. You get the carbonyl on this side with this carbon here in the middle, and that's going to form an aldehyde as well. But if I bump it up a little bit to something a bit more severe, like a KMNO4 and H2O and heat, this can break open our double bond and it will actually over oxidize in such a way that as long as you have at least 1 proton on either side, well, one side could be completely an R and an R, but the minimum criteria is as long as there's at least 1H, then you can get a full oxidation of this and it will turn into a OH alcohol functional group. So let's break that apart real quick. So let's draw a line right down the middle, open it up. So again, if this was an ozonolysis and it was O3, you could stop here and that would be the final answer. Aldehyde over here, formaldehyde over there. But you can over-oxidize with a KMNO4 and you essentially sneak in a proton, so you sneak in an oxygen next to the adjacent H, and that's how you get a carboxylic acid on one side, and you can get a carboxylic acid on the other side. Something like this.
Mm.
So this would be called formic acid. Again, sometimes, like a formaldehyde is like the most basic type of aldehyde. This would be formic acid for a carboxylic acid. Um, Usually don't have to memorize too many of those names, but okay, so that's how that one works. No mechanism, thankfully, so we just kind of need to recall that one and have a couple tricks up our sleeve on making carboxylic acids. There's another one that we learned actually in the chapter 17 and 18 land, starting with aldehydes and ketones and constructing a carboxylic acid. I'll give you a second to think about it if you can recall. If not, I can give you one more hint.
Is it MCPBA?
Perfect. Yeah. So there was a little trick with the MCPBA, right?
Mm-hmm.
And basically, how it works is you're going to sneak in an O on if there is a proton present, you're going to sneak in the O adjacent to that proton, right? So if there's an H here and you have a decision to make, right? It's like, am I going to put my oxygen over on this side or am I going to put my oxygen on this side? If there's a proton present, then the proton will always win. Right. So then you're going to get the oxygen to sneak in on this side. If there was no proton present, then you'll have that preferred tertiary is better than secondary is better than primary type of comparison. But that was with starting from a ketone. Here we're starting from an aldehyde. So if you start from an aldehyde and do MCPBA, you have the ability to make a carboxylic acid. But if you start with a ketone, you're limited and you can only get as far as making an ester functional group, which is one of the children or one of the babies from our carboxylic acid reactions. But yeah, that's a good one too. And I'm completely blanking on the name of it's like, oh, migratory aptitude. There it is. Right.
Mm-hmm.
That's the decision making there for tertiary better than secondary, better than primary, but H is better than all of those. Okay. So that's called Bayer-Villiger, by the way, another key term there, Bayer-Villiger reaction. Okay, so that was another one. This will be good review, and this goes back to also the last set of reactions that you had from the previous course. So for that reason, I won't give you too much context and see how we do. So let's put this here, and then let's put this one here. Okay, and then let's react this with something like HCl, comma, KCN. All right. Pause
Mm.
there for a second. Let me know what you think. And I think most importantly is kind of like the first steps.
Okay, so let me finish copying this
Mm-hmm.
down. We have a double bonded O. We have the double bond, which can form resonance.
Mm-hmm.
And we have HCl and KCl. Okay. Mm, 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 mm. So when I see the double bond next to it in the allylic position, it makes me
Mm-hmm.
think that we can move it or move the electrons in case we need to. Well, in case we need to, like we can move the double bonded up, we can push it onto the O, we have the minus with the positive. Um,
Mm-hmm.
and then let me think about this. And then I know we're gonna end with the triple bonded C to the N.
Okay. Yep.
So in this case, are we gonna have the double bond break out to go grab the C?
Oh, I see. Which double bond? Like this guy?
Yeah.
Okay, good suggestion. So when we do stuff like that, because that will come back up in a couple chapters, um, when you had to do like aldol condensation,
Yeah.
you'll do something called Claisen condensation that may have come up for you, but it really comes up a lot for this class. My point being is what you're thinking is if this were to come down, then this guy's hungry to go grab somebody, right? So that is definitely a good rule of thumb, but we have to consider that these are resonance structures and the fact that we formed a positive sign created a lot of deficiency. So I'm like more so looking at this region saying, "Oh my gosh, like should I do something there?" right? Or I'm looking in this spot saying like, if I had a strong enough of a base, it would bypass this 1-4 system and it would just head straight into town, you know? So this goes back to 1-2 versus 1-4. The strong bases like, and it's still important for this class. Your strong bases are going to go attack the carbonyl regardless of any system that's next door. And that's for your carboxylic acids too, unless you are in that presence of a strong enough base. So, for example, if you're comparing like an NaBH4 versus a lithium aluminum hydride, your LiAlH4 is going to want to, possibly go grab that proton and deprotonate it. But if you're something like an NaBH4, I might be able to go into that carbonyl carbon. But my
Gotcha.
point being, because really that is lower yield. The higher yield, though, is this system here and the KCN specifically with acid. So why do we care about that? Because I'm trying to make a carboxylic acid. So KCN's not a strong base, right? Although it's CN minus, it's not going to want to come into here and just like attack, right? So it's not going to do that. So instead, it's going to be patient, and now it's going to want to go here. So now you're CN minus, C, triple bond N, one lone pair on the N, one lone pair on the carbon, negative sign comes into here. And then, of course, because our first step, actually, we were in HCl. And I know you didn't say to put a negative up on top, which is good. But the O up on top is going to grab a proton. So up there on top, the oxygen's already going to be protonated, and then the C is going to come in. So then you have your CN, and then we'll go from there in just a second. All right. So let's say that went into here. Your O up on top is neutral. And then on the side here, you have your new CN group like this. C triple bond N. All right. Quick recall. What is the name of the process that's going on over here?
Oh my God, it's enolization.
Perfect. Yep. Right. So our enol will tautomerize to the keto group, right? So on top, that's going to go back to a keto. Kind of confusing, right? Because we're talking about carboxylic acids. Up here, this will form a ketone. Okay, so there's that. Okay. So that's taken care of, right? Because the pi bond grabbed the H and then you made the double here. Okay, so that looks pretty good. Now, one other thing with our CN group, and then we can kind of go from there. But yeah, so let's do that. So with the CN group in the presence of enough acid, so typically the way it's set up right now is technically enough, but your professor likes to create problems where you have like, hey, here's step one, step two, right? And then you have to produce an answer. And then it will be clear there's one more arrow and one more empty box, and you need to fill in the final product that they're looking for. So that would be nice, to be honest, because it'll give you a little bit more like, okay, I'm supposed to do something more now. And then at that point, you would bring in the H3O plus. And this is where one of our reactions to the carboxylic acids comes into play. And this came up prior either at the end of 118B or even I think doing some 118A stuff with like SN2 type of stuff. But this is where an H3O plus comes in with a nitrile, and then we form a carboxylic acid. I'm going to pause there for a second to field any questions because it may not seem like a loaded question, but I feel like I dropped a loaded question there with the cyanide and the H plus, and then it magically turns into a carboxylic acid. So if you have any questions, feel free, and then we'll talk more about that in a second.
Hmm.
Okay. Any questions with that?
Maybe. So I
Maybe.
understand how
Yeah.
we get to the C triple bonded N.
Yes.
And then from there, do we have, because obviously there's a partial negative on the carbon, right? Because it's being tugged on by the nitrogen.
Partial positive.
Partial positive, yes.
Uh-huh.
Is that gonna get attacked to kick off the N, or do we have to do something like we did where we have to make like an N2 gas, like bring in another equivalence?
No, that's a great question. So this will set us up well because we have, well, I like to say we have time, but since it's summer session, we kind of don't. But we have time to wait to fully answer this question. But what I used to do is not bring this up at all. And then we just like talk about it when we get to nitriles, which is the last set of reactions of all the carboxylic acids. I don't like doing that anymore because it was too late, right? And then like the
Mhm.
exam would happen, and like this is one of the harder mechanisms. So to understand at the beginning, you're pretty dang close, right? So nitrogen has a lone pair. It's gonna go grab the H. Perfect. Again, we're not gonna fully do the mechanism. We're just gonna understand it enough. So when the N grabs a proton, then this N is gonna become positive. The reason why that's good is because there's a bunch of pi bonds next door, and you know pi bonds can move. And so when one of those pi bonds moves over because the nitrogen was positive, then what happens, right? Our partially positive carbon is now fully positive, like a formal charge of +1. That's awesome, right? Because what happened over here? When the N hit the H, this was H3O plus, but then we're going to have H2O floating around. H2O, poor base, it's a nucleophile. That thing can come in, and now you have an addition of a oxygen connected to carbon. And you can see here the main goal is to get rid of N, right? But
Mhm.
also see that there are two different equivalents of oxygen. So
Mm,
understanding that this is like exactly what you brought up, where it's kind of like, are we making an N2 gas? Close. We're going to make an NH4 or an NH3 plus, actually. And then it gets booted out and it's neutral, like as an NH3. So it's kind of like that N2 gas mechanism, but the reason why it's different is because we're not bringing in another N. So we're not going to like try and form an N triple bond N. Instead, we're trying to break this triple bond progressively, like one pi bond at a time until it's single bonded. And every time the N grabs an H, a water group hits here, right? So then N becomes neutral again. And like, hey, I'm doing great. And then it grabs another proton, and then we break another pi bond, and then your second water group comes in. And I think with that knowledge, it will set us up nicely for when we do the derivatives of carboxylic acids and get to nitriles, and then we can walk through that mechanism.
okay.
Yeah, but overall, I would say most students just like don't even get to it at that point, especially in the summer. So if you can like get to that point mentally before the exam, you're going to be in a good place because that's a lot of points and it's like one of the later reactions. And as you know, sometimes professors can fall behind on their schedule, right? And then it's, you just don't want that. So
Right.
we'll kind of jump on that ahead of time. Okay, awesome. All right, so that's that one. Okay. So yeah, so far so good in terms of, oh, I think I copied this for a reason. So now I'm going to paste this real quick. Okay, so one thing I'm going to do real quick is now I'm going to get rid of this double bond and we're just going to see what happens because of that. So, and without doing any work. So let's say there was no, let's get rid of all of that. Let's say it was still HCl, KCN, but in this time there was no allylic, right? So of course then, mechanistically again, the O is going to grab the H, no problem. There's going to be an OH up on top. This is partially positive, so then your cyanide group is just going to want to go in there. And then again, imagine there's like one little intermediate, and then you just continue to draw your mechanism. And because the cyanide group hit at that spot up on top here, so this is a cyanide for a split second, when you react it with the H3O plus, then your carboxylic acid is just going to be completely adjacent here. So I'll actually draw this intermediate to the left and then draw the carboxylic acid on the right. So then the cyanide turns into C double bond O, OH. And so this is an interesting one because what's different is at essentially the same carbon of interest, you have both two new functional groups. So you have an alcohol functional group plus a carboxylic acid. So that's pretty cool compared to the last one. We were like pretty far, pretty separated from the ketone group, and it ended up staying as a ketone. And then our final answer included a carboxylic acid. So kind of unique little situation there. All right. There's a couple others from, so I'm just gonna write them. We're not gonna do them because I find that these are such low yield and there's no mechanism for them. Possibly they'll come up when you're doing lab stuff. Do you still have a lab over the summer for 118C?
Yes.
Okay. So these ones you'll probably see on the lab. Again, for me and my brain, these are like 5%ers, less than 5% in terms of what could show up on the exam. But these also help do construction of carboxylic acid. So if you start with an aldehyde, and depending on whether you have a Tollens or a Felons reagent, you ultimately get to the same answer, and that's to produce a carboxylic acid. So if your R group on the left, your H over there on the right become over-oxidized, and you can make a carboxylic acid. No mechanism or anything, but I do think it's important to at least bring it up. One other one is called the iodoform test. Again, to me, sounds more like a lab. And so you might see this in the lab, but you have this, and then you have I2, and then there's OH minus. And again, not really any like full mechanism. We could probably, you know, make it up as we go. There's probably some reasonable mechanism steps, but for what I know, and in terms of what's probably going to be on the exam, this is again, I kind of loop these together as pretty lower yield type of things. Um, but the only cool thing about this one is you do make a leaving group that has a C with some of the iodides. So essentially what you're doing is if you have an R group on the left and you have an R group on the right, the minimum criteria is you need to have at least one carbon that's fully CH3. And you can use the entirety of that to kind of break it down and lose essentially all of the bonds and the connections so that you can have additions of iodides to it. And again, the main point is we're trying to make carboxylic acids. All right. Now we can jump into some new stuff, which is exciting. A lot of that was review, but obviously early on, it's like the alkene mechanisms, and when you got to 118B, your first exam, in my opinion, it feels like half the test is still doing like E2 reactions from 118A. So
Totally.
similar concept here for the first exam, at least for the first half of the test. All right, so let's do a couple together, and then we'll kind of ask you some questions along the way, because some of these you will know the answer to. So let's say I have something like CH3, CH2, Br, and then I react it with Mg and diethyl ether. That's our first step. And then you can tell me what we make, and then we'll keep adding steps.
Okay. So we're gonna insert the Mg. So it's gonna give us CH3, CH2, MgBr.
Perfect. You can see we're making that Grignard reagent. So now we have our RMGX. Then our step 2 is a CO2. Again, pretty similar. We've seen it at some point. It kind of is sprinkled along 118A and 118B. But now we bring in our CO2. What's going to happen there with our CO2?
Okay, so we have C double bonded and it's going to attack and it's going to break off and we're going to add CH2, CH3 to that carbon.
Yeah, perfect. Right. So this bond in here is reactive. It hits the carbon. This pushes up to a O minus. I kind of start to redraw things, and I think of like a C, double bond O up on top, O minus, and then your new carbons. So we have 3 carbons in total. Here's my CH3, CH2. And then, of course, with our next step, we have an H plus. That's going to help us turn that into a carboxylic acid. So again, another way of building a carboxylic acid, especially from some of these older reagents that we're familiar with. Now here is our carboxylic acid, just like that. So again, you can use some of those more fundamental things that we've learned, like Grignard reagents. You could use RMGX or RLI, organolithium, for this mechanism, react it with CO2, and you're able to make a carboxylic acid. Okay, as long as we have that H plus to help, um, feed that O minus, that acid workup. Cool. All right. Okay. And then let's bring in a benzene ring. You can see a lot of overlap with some of the older chapters. They can start to bring in some of those older reagents, older functional groups too that we spent time with. Okay, so let's say we have a benzene ring, and then we have our, let's do like a CH3, and then react this with KMNO4, kind of like a reagent we saw earlier, actually. So KMNO4, H2O, and then heat, and then we can follow that up with some more acid workup. Okay. Any thoughts on this one? This is actually, I think, our last older style of reaction. Then we just jump straight into carboxylic acids.
Okay, so with KMNO4, it allows us to over oxidize. We usually cleave at the double bond.
Mm-hmm.
We have a benzene ring. I'm trying to. Do we open up the ring?
Good suggestion. I would say anytime for the purposes of 118C, if you have a benzene ring, we're probably going to end up just keeping it closed. So, and then I'm going to do a couple follow-up questions here too, just so maybe it'll probably spark your memory. So let's do this, and then maybe let's compare and contrast and see what happens if I had something that was like this instead,
Ah, damn.
right? Mm-hmm.
Okay, so the methyl group is an ortho para director since it's donating. So are we gonna add a carboxylic acid to the ortho or the para spot?
Okay. Also, good suggestion with ortho-para meta reactions. Can
Mm-hmm.
they show up for the first couple of tests? Maybe, but for our midterm 3 content, we actually jump back into benzene rings again, and then we do carboxylic acid reactions and mix it with benzenes and see like all the chaos that happens, especially with orthoparameta type of reactions. So
Gotcha.
at least for right now, you could probably not have to do any type of review fully with some of the benzene ring reactions. So that's a good first step.
Okay.
The KMNO4 is an oxidizing agent. And kind of what I'm going for here is comparing, hey, this is pretty dang bulky and this is not. Now, that could lead your brain in one way that you're probably thinking, and, again, not as concerned about, hey, I got to do para only type of thing. Instead, I'm looking for, do I at least have one benzylic carbon? Okay, we have a benzylic carbon for both of these. And that's the first one that's coming off the benzene ring. And then at that benzylic carbon, do I at least have one proton available? And if I do, I can completely convert that entire carbon into a C double bond O and then an OH alcohol. So then we have our carboxylic acid just like that. But if you're at that point where it's so branched and the benzylic carbon doesn't have a benzylic H, then we have that limitation where we're unable to make the group that we want. We're unable to make that carboxylic acid. And so we end up getting a no reaction. So then a couple others, just to follow up with that, again, I could make this if this was 2 carbons or 3 or 4, right? It doesn't matter. There's no like rearrangement that happens. There's nothing weird. You just still make the carboxylic acid again. If I'm branched and I have, this is now more of like a secondary type of carbon, then that carbon is still able to make your carboxylic acid because it has one benzylic proton hanging on for dear life. So again, once you get into the isopropyl, well, this is isopropyl. Once you get into the tert-butyl, then we have inability to make our carboxylic acid.
Gotcha.
Awesome. Okay, so really, if you think about it, you can make a carboxylic acid from an alkene. That's important because that covers your chapter 12, chapter 13, and chapter 14. Anything to do with a pi bond, simple kind of double bond type of thing. You can make a carboxylic acid from an aldehyde. Okay, that's chapter 17 and 18. You can make a carboxylic acid from a benzene ring, and that covers your chapter 15 to 16. So that spans the entire 118B course. And then from 118A, some of the basic fundamentals would be just like doing a simple SN2 reaction, then maybe doing like a PCC or doing a Jones. And then, from there you can do a full oxidation. And so that kind of covers 118A as well. Okay. So now we've kind of covered all the chapters in terms of what you need to at least get you set up. That way you don't feel like you need to go fishing through all of your notes from 118A and 118B to make sure you feel successful here. Definitely not the case. There's only a few reactions and then, mainly just focus your efforts on the new stuff.
Okay.
Okay. So now I like to do a little flow chart. So let's say we have our carboxylic acid. We've finally learned how to make all the different types of carboxylic acids, and now we're moving up in the world and we're using our carboxylic acid and making a bunch of cool new things. And so some of the cool new things that you can make are called alkanylyl halides. Another term for that is simply acyl-halide. I honestly prefer acyl-halide, but you'll hear alkanylyl halide sometimes. You can make esters. You can make anhydrides. You can make amides. So these are probably all functional groups that at this point you've heard of, but really we haven't had a lot of experience with these functional groups. And then the other thing you can make is an alpha halogenate. So what that means is we have next door, it's kind of like the alpha carbon chemistry. Next door to our carboxylic acid, instead of having an RCH2, we can take one of those protons, deprotonate it, clear up some space, and now we can add a halogen to our alpha spot, right? So again, alpha is always that first carbon adjacent to a carbonyl. So that's our alpha carbon, and we have a halogen there. So that's another new thing we can make. And then lastly, I put this last because it's going to be the first thing we start with. The primary alcohols is something that we can make directly from a carboxylic acid. Now, from a carboxylic acid, can we make other type of alcohols? Probably, but directly, the main thing that we can make from a carboxylic acid is a primary alcohol. And then if you needed to like spice it up a little bit and like make a secondary alcohol, then you'd have to get creative, and then at that point you would oxidize it and then bring in a Grignard, and now you have your second R group, and now it's reduced, and then you make a secondary alcohol. And then from a secondary alcohol, you can oxidize that again, do another Grignard or an organolithium, and then you can make a tertiary alcohol. So all of that stuff is kind of how I want you to think. I never thought like that when I was a student. I just like purely regurgitated what was on the notes and just try to memorize it hardcore. But if you can always be plus or minus like one or two reactions, then you won't be caught, not knowing something. So that's my mentality. Okay. But directly from a carboxylic acid, I can't make a secondary or tertiary, straight off the bat. Okay. Now, in terms of reduction, I know earlier we talked about, and again, this is sort of like that 5% rule. Notice how here I'm going to put LiOH4, and we're going to put a disclaimer. So I've seen this two different styles. Style number one is it takes a proton here, you get an O minus. I will say that can happen. And if you are looking to have an answer that is a deprotonated carboxylic acid where you didn't do anything fancy, you didn't make a new functional group, and all you did was deprotonate that carboxylic acid, I would react your carboxylic acid with something like a Grignard or an organolithium or an LDA, something super strong like a base. If you want to reduce your carboxylic acid and turn it into a primary alcohol, then I would advise using specifically the lithium aluminum hydride with the diethyl ether and then an H plus. And so this would be a good um, office hour question that you can bring up. And I think it will show your professor, hey, that you're pretty knowledgeable. And it also kind of pushes that limit of like, this is a hard question. I'm surprised that you're coming to me with such a difficult question, right? But it will also give you more clarity so you know for sure. So my main take home point is this definitely works. So if you need to do it, go for it. If you see it, don't do the deprotonation here. Go for the full reduction and make that guy. All right, that's my main take home point. And then I am going to add the RLI and then the RMGX. And then that will deprotonate, something like that. And the reason why I actually bring up the RLI and the RMGX in this flow chart, because in years past I did not. I bring it up now because it is actually a good talking point showing you that what traditionally lengthens a carbon chain and adds a new R group, this is kind of our first time where we run into a roadblock, and that actually didn't happen. Now, if you need to lengthen the carbon chain, that's where we get really creative with these flowcharts. And a synthesis problem, for example, can lead you in the direction of lengthening the carbon chain. So, for example, let's say this was an RC double bond O with an OH alcohol, and your synthesis problem was to be like, hey, I want to make an RC double bond and then an R prime, right? And so it's saying, I want you to do organolithium, right? I want you to bring in a new R group. Well, we can't do this directly. We already know that's going to be an issue. So what you can do instead is you go through one of these alternate routes, you make one of these cool new guys, and then the benefit of making these new reactions is you get rid of that proton. So for example, let's look at an ester group. An ester is going to look like this, right? RC double bond O, and then that R prime group can be the same R group, but oftentimes it's going to be different. So I like to put a little prime.
Mhm.
Now, from here, you can do that reaction, RLI or RMGX. Put in some diethyl ether, follow it up with some H plus, and you can treat this again like a replace the box method. So here is our leaving group. All we're going to do is replace the box. And who are we going to put? We're going to put our new R prime group that comes into town. So there's a lot of benefits from starting here, and this is where we start your whole entire chapters on carboxylic acids for chapter 19. Chapter 20 are the derivatives, right? So there's a lot that you can learn from here, but just knowing that the proton is like your best friend, but also your worst enemy. If you get rid of it, you can do more creative things as well, and you don't run into that problem with the proton. So now we lengthen our carbon chain. So it is possible. We can lengthen our carbon chain. Okay. So let's throw in our reagents now. So we talked about our lithium aluminum hydride. We can throw that guy in. That's no problem. We talked about that. And then our next one that we can do is we can construct our acyl halide. Do you happen to know maybe like what reagent we might use? Again, I know you're just starting, so I'm not expecting you to know it, but we have actually seen the reagent before in the course past. Any ideas with our acyl halide production?
Well, I know an acyl halide is the C double bonded O with a halogen.
Perfect.
So I'm assuming we're going to need a halogen somewhere in our reagents.
Somewhere, right? Yeah. You've seen a lot of BR2, you've seen a lot of HBr, that type of stuff.
hmm
The other type of halide that's come up is with your alcohol reactions from chapter 9. And we saw stuff like SOCl2, right? We saw PBr3. So those come back. So here we could do SOCl2 or PBr3 or PI3 because again, what they teach you in class is SOCl2. But then you're on an exam and you see carboxylic acid plus, and then these weren't reviewed in class. And you might be able to piece it together because you probably are good enough with SOCl2, but sometimes again, you just don't study it, and then you're like, oh crap. Does it do what I think it does? Maybe, but this is for sure. So SOCl2 will make the chlorides, PBr3s and the PI3s will make the Brs and the Is. Okay. There is a mechanism for that. So we're going to do it, but we're not going to do it today. We're just going to kind of have our whole flow chart here mapped out for us, and then we'll go from there.
Okay.
But you'll see SOCl2 without anything, and then you'll also see SOCl2 with something. So you might see SOCl2, comma, and then they do like a pyridamine or I always forget. I think I'll have to look it up. It's either a pyridamine or a pyrimidine. I always forget. I don't think it's a purine though. So it's this though. So you're gonna have the nitrogen here with the lone pair. And the reason why that's important is because if you do SOCl2 with nothing else, somewhere in the mechanism, you actually make an HCl. And that can be dangerous and, for lab purposes, okay, cool. Thanks for letting me know. I don't want to blow up the lab. But for your purposes on an exam, it's important because if you do make HCl, she could ask you a question on like, why does this not work? And oh, it's because you form an HCl. And then what would be a solution? But if I do SOCl2, and this pure I'm gonna have to look it up. It's gonna drive me crazy. The pyrimidine, then we bypass the production of an HCl, and this actually saves the day mechanistically, so you don't have any issues. You don't make HCl. So, little pearl. Okay, and then let's do. I think we have time for like one more, and then we should be good. So for the anhydride, oh no, we're on the ester. So for the ester, you can do R prime, OH, comma, H plus. That's one of the more popular mechanisms. For the anhydride, you can do a R, C, double bond O, OH. So you basically take two carboxylic acids and you bring them together, and that's how we form an anhydride. So the anhydride actually was my least favorite as a student, this one. And again, these can be symmetrical or they can be asymmetrical. So I'll put the prime. And then your amide, you just bring in any type of amine. So I'll just do a basic one with the nitrogen and then H3. And you get RC double bond O and then NH2. So again, all this is a replace the box method. We replace the OH with an X. We replace the OH with an OR. We replace the OH here with our other carboxylic acid, and then we replace it here with an NH2. And then we'll do this one more on the later side because this one is a longer mechanism and is the hardest out of all of these. But this sets us up nicely. You can let me know how lecture goes, and if there's any other little nuances, we can throw it into our little chart. And then from here, what we'll do is we'll continue to expand upon this because each of these will have their own flow charts too. So then from an acyl halide, we need to learn all the 10 different reactions that happen from there, et cetera, et cetera. So that's our game plan. Okay.
Okay.
Awesome. Okay, cool. I think we're set up well, and we will go from there.